can wait for a minute or so. Couple of my graduate students are joining now, so.
Welcome, everyone. We're going to wait a few moments for others to join us, and we'll begin soon.
So welcome, Rajesh. Rajesh joined the program. Prabhakar to join us.
Welcome to the Alumni Lecture Series. My name is Heather Belgian with the YSU Office of Alumni and Events. It is my pleasure to introduce our moderator today, Dr. Suresh Sharma, who is Associate Professor in the YSU Department of Civil, Environmental, and Chemical Engineering. Dr. Sharma, thank you for joining us.
Thank you, Heather. Good afternoon and welcome to you all in this Alumni Lecture Series hosted by Office of Alumni and Events at YSU. As Heather mentioned, my name is Suresh Sharma. I'm an Associate Professor at YSU. Today, I would like to invite an outstanding alumni, Mr. Ken Kagy, who is going to present his research in a hydrologic area. Let me briefly introduce Kagy. Mr. Kagy graduated from Civil and Environmental Engineering program of Youngstown State University in 1979. Over the last 40 years, Mr. Kagy has accomplished so much in civil engineering and hydrologic research. He worked for several companies, consulting firms, and the local governments. He is currently working as a civil engineer at the city of Milton, Georgia. Mr. Kagy has a wide and diverse experience, including but not limited to floodplain management, stormwater infrastructure design and construction, community floodplain outreach. He's a licensed professional engineer and certified for various other disciplines. Today, he's going to present his research, and his research topics is an Archimedean estimation to hydrology time calculation. I would like to note that we'll have a question and answer session after his presentation. Mr. Kagy, it's our great honor to welcome you, and I would like to request you now to present your research. Thank you.
Thank you, Dr. Sharman. I appreciate that introduction. That was a nice introduction, and I'm glad when I first met you, you reminded me that I was just graduating from YSU when you were, I think, graduating from first grade. So I'm glad you didn't bring up my age. So I know that's always a tough subject to talk about. All right, so let me pull this presentation up. I've done this presentation for the last 5 or 6 years. Um, and this is the first time I brought, and this has evolved over the years actually, over that time. Don't I brought in this Archimedes idea because I was studying him the other day, and I realized that some of the things that he did was pretty close to what I was trying to do in this time of concentration. So I just brought it in the beginning, but this is certainly not the way I initially started this research or this idea. I just kind of fell into it after reviewing like thousands of hydrological reports over the years. This just kind of came to me. But anyway, just a quick history here, just kind of a different approach to what I'm going to be talking about. Archimedes was a mathematician, and he was credited for systematically approximating pi. And the way he did that, he developed a technique. Pi was well known back then, like 3,000 years even before Archimedes. They knew there was a ratio between the diameter of a circle and the circumference of a circle, and they knew it was around 3, but they didn't know exactly what that number was. And so he devised a technique. He circumscribed a polygon about the circle and inside the circle, and then was able to use um, he was able to use Pythagorean theorem to estimate the edges of those triangles. He drew triangles from those polygons, and in doing that, he took he obviously the more polygons you have, the more accurate that estimate is going to be of the circumference of that circle. And so I think he started out with a six-sided polygon and divided it up into 6 triangles or 12 triangles, and then kept increasing it until he felt he had enough triangles in there to really estimate the arc of the circle a little bit better. And back in about 250 BC, he had a 96-sided polygon, and he estimated, based on the outside polygon on the inside part of that polygon, that was 22 over 7. The pi was somewhere between 22 over 7 and 223 over 71. And that was like within a 0.01% accuracy, which is amazing considering he didn't have a calculator. In fact, they didn't even use decimal points back then. So they all had was fractions. So he did some. He was mathematically, it was a pretty ingenious idea, and he did some other things. He's also known for the Archimedes theory, basically, where he used the king's. The king was concerned that where his crown wasn't completely gold, and so he was able to submerge the crown in water and estimate the density of the jewels and the metal in that crown, and he did things like that. It was just amazing. He was probably the original master of rational thinking back then. But anyway, let's talk about the let's see. You're probably wondering how would this really apply to hydrology. So we'll look at the hydrology here. And I'm going to start from some of the basics. I know some of the audience out there really understands these fundamentals, but sometimes I have people in my audience that don't understand the basics of hydrology. But factors affecting stormwater runoff, surface conditions, soil type, the watershed size, the length of runoff, basin slope, and then rainfall depth. And those are all different factors that's going to affect this. What we're going to look at in this study is 4 different types of surface runoff coefficients that are commonly used. We're going to evaluate and compare those runoff coefficients. We're going to use NRCS's segmental equations, sometimes called velocity equations, and we're going to graphically display those and show what those really look like. And then we'll look at 3 different time of concentration empirical equations, and compare all 4 of these equations in graphs. So this is the basic definition of time of concentration. Well, basically, time of concentration is the time required for the most remote hydraulic distance in the watershed to the point of the basin outlet, and that's a fundamental part of hydrology theory, and it's certainly important into estimating peak flows because time of concentration is necessary in the calculations, that all calculations used in hydrology. And so, in fact, I've talked to other professors about this subject, and they say that's probably the least most understood parameter of hydrology and where most of the errors are. And I see that in my thousands of reviews of a hydrology report. There's just lots of errors in this particular area. So first one we're going to talk about is velocity equations and RCS segmental equations. You got the sheet flow, shallow flow, and open channel flow on a watershed basin. First one is the sheet flow, and that's really estimated by the Manning's kinetic wave equation. And here it is, the equation itself. Most of you are familiar with it. And it's a very common equation used for stormwater runoff in a lot of areas. So these are the Manning's coefficients that are used for sheet flow, which are different than Manning's other coefficients used for channel flow, because NRCS considers sheet flow to be less than 1/10 of a foot. And so that's a significant difference in the type of coefficients you would use. And I've seen in practice, people don't differentiate between those coefficients sometimes. They're using channel coefficients in sheet flow into channel flow. And it does create a little bit of a problem. There was over the years in 1982, Kibler and Aaron indicated the maximum flow length is less than 100 feet for the sheet flow. Dr. McCurran, I've spoken to on this particular project, came up with this equation 15-8, and it's in the National Engineering Handbook. And it gives you a rough estimate for the length of flow that you would use for sheet flow. Not many of the people practicing or do the hydrology reports subscribe to this. It does have its issues, especially on impervious surface. It's not real accurate on pervious surface, but it does a pretty good job on, on pervious surface. On impervious surface, it's a little bit more accurate. So what I did is I took the Manning's low value for sheet flow and the high value. I just came up with an average, and I knew what that related to percentage-wise for with an impervious surface and a very pervious surface. And so I took the extremes and I plotted that out just graphically, just to get an idea. So what I'm trying to do is just get a reasonable distribution in your n values. It doesn't, I mean, I just want, they may or may not be evenly distributed, but I just wanted to get an idea of where these n values fall between the extreme, between a 1% impervious surface and a 99% impervious surface. And so I used an exponential, linear, and polynomial equations, and I averaged those out. And so I just re-plotted that out and got a fairly reasonable distribution. Next, we'll go into shallow flow, concentrated flow. And the engineering handbook has has a chart in there for different types of runoff, surface runoffs. And NRCS considers shallow flow to be from 1 inch to 6 inches deep. That's what they consider shallow flow. And so they have created some of these velocity equations based on that depth. And this is from the engineering handbook. And so I just took, and you can recalculate these velocity equations. It's just taking Manning's n value and the depth and coming up with a B equation from Manning's equation. And so I established a whole set of velocity equations based on my distribution of my n values. that I just recently calculated, and a flow depth of a quarter of a foot, a little bit deeper, but not much. Open channel flow, this is Manning's equation, and that's usually what's done. But what I've found in practice is that most people don't really know their channels that well in the basin. And so they're just taking an average shape and size of the channel flow and guessing that that's what their channel is going to be. But obviously the channel is going to change as it runs through the basin. It's going to change in size. It's going to change in width, and it's going to change its characteristics as it goes through. But I'm looking at some smaller watersheds here, and so in these smaller watersheds, you can do the same thing you do for shallow flow, as long as the flow depth is um, small and wide in the channel. And so we were going to take that assumption. Then you can do the same thing. You can create velocity equations. NRCS considers anything over 6 inches or deeper to be channel flow. I did an initial 8 inches and increased it up to the maximum of my watershed size, up to 16 inches of depth. So I had an average about 1 foot depth. And that's, if 18-inch pipe inside a watershed basin, that's a pretty reasonable assumption. These are Manning's N values for channel coefficients here. Most of you are familiar with them. And so then I went through and calculated out these velocity equations based on Manning's N value and initial flow of 0.67 foot, and then of course 1.35 feet of depth. So in calculating hydraulic time of calculations in the velocity method, you take all 3 of these, sheet flow, shallow flow, and channel flow, and you add them all together. You sum them all up, and that's what you use for your time of concentration. And I can tell you 95% of the reports I see use this method right here for calculating their time of calculations for time of concentration. And it has its issues. It's certainly the big issue it really has is the sheet flow. And there's been a lot of debate on sheet flow. We can discuss that later on, but that's one of the biggest issues you have. So I'm taking McCurran's equation here, and I'm limiting my sheet flow basically 90 to 110 feet for my more impervious surface, and then I'm dropping it down 10%, just as my increments of the surface conditions also drop down by at least 10%. Remember, I distributed out even 10%, the 1, the 10, the 20% impervious. And same with the shallow flow. So I did 400 to 500 feet, which is what the National Engineering Handbook recommends for length, is about 3 to 4 times the sheet flow. And in actuality, if you want to get an accurate measurement, you should actually go out and visit your drainage basin and actually take some of these measurements. But I assure you, nobody really does when they do these calculations. So so now we're going to try to visualize this. So the remaining flow path was considered channel flow, the deeper flow, and the equations are considered flow are the path geometry, slope, and surface conditions are all considered homogeneous. So what this looks like when we plot this out, if you take the extremes here, we have a 1% slope at 1% impervious, which is very pervious surface. And at the bottom side, I took a 12% slope at 99% pervious. So now we have some boundary conditions here with time of concentration, because we know that probably the majority of our time of concentration is going to occur between these 2 boundary conditions. There's going to be unique situations out there where this may not happen, but 95% of your hydrology studies are going to happen within these boundaries. So what we want to know, or what we want to find out, is what's in between here. What's in between those 2 lines, and how do we fill in? How do we find out the information between those 2 lines? So these are some of the basic assumptions I used. High impervious surface basins are defined by the lower graph, and then of course the pervious surface are defined by the upper graph. And of course, this is where most of your time of concentration occurs. Following were interpolations for relationships of percent impervious using the CN value, the C value, and N values. And then I just basically calculated those out using the velocity equations based on my distribution of those values themselves. And so here's your CN values. This is a common chart for CN values. And I took an average. Um, so I took it for all soils types, and then this is a standard chart that relates to the percent impervious for the different CN values. It's in the engineering handbook, NRCS's engineering handbook. So with that, hang on, there we go, sorry. I did the same thing with C coefficients, soil types. And you can see I had some difficulty with the C values because C values seem to be area oriented. And everybody puts everything in the C values. I found that C values are not as well defined as CN values. Let's put it that way. That's the easy way to put it. They incorporate slopes into C values. They incorporate, of course, these are the common. You can see the common percent impervious surface based on the same description you saw in the CN values. So we can relate those C values to the C values based on this table. This one happens to be from Pennsylvania State University, and I think it's pretty much generated for that area up there. So then I took the related the percent imperviouses with those soil groups for C values, and then took an average for all those C values. So then now we've got a relationship. These values are plotted in the following graph. So now we've got a relationship between CN and C values. And here's what it looks like. So now we've filled in that blank between the two extremes, those two boundaries that we saw, where you got the maximum impervious and minimum impervious surfaces. And this is for a 2% slope, time of concentration calculated out with velocity equations, with all the information I just told you about. Here's what 5%. So you can see this, the curves are starting to compress, which makes sense. Obviously, the steeper the slope, the faster the time of concentration is going to be. This is plotted in flow path and feet per time of concentration. Here's what 10% looks like. And so now you can see they really start to compress. But we have something to compare to with N values and with CN values and C values. They're all, we can relate them now, and with impervious surface. Everything is tied back to impervious surface. Another equation I looked at was Kirpich equation, which is a somewhat popular equation, but it's set up primarily for smaller watersheds, 1 to 112 acres. And it was studied for 7 rural watersheds, and it had a basin slope from 3 to 10%. So the area or the study that it was done on was pretty much the type of basin that I was looking to do some comparison with. And this is the equation. So you have a length in there and you have a slope. So I plotted that. The problem with the Kirpich equation is you can see here, Chow had some values for overland flow for natural grass, overland flow for bare soil, and flow on concrete or asphalt. The problem is I didn't really have anything for wooded areas. You don't have anything on the high areas. So, but I related these based on the description to the same percent type of surface, percent impervious surfaces for an estimated C value, estimated CN value, and estimated percent impervious. And so I plotted those out, and I'm calling the K value. So what we don't have is a K value for the Kirpich equation on the wooded end. So we're going to have to extrapolate a little bit, which is sometimes a little dangerous, but we didn't have to extrapolate too far, so hopefully it's not that big a risk. So now I compare I calculated this out just like I did with the n values. And so as you can see, I did the linear and exponential and polynomial equations, and I came up with an average for each type of percent. And I did just from the initial 3 plots there. And so then when I did that average, recalculated it and replotted it, I came up with now an estimate for a 1%, which is about a K factor of about 3. That's the area that we don't really have any research on. So we just kind of projected it out there from extrapolation. So now I've got a table that can relate impervious surface to CN values, to C values, to Kirpich K value, and the N sheet flow coefficients. And you can see here's this table. So now when I could plot Kirpich to velocity equations for time of concentration, this is what Kirpich looks like at a 2% slope. So you can see there's a systematic crossing with Kirpich and the velocity equations. Again, it's flow path to time of concentration. Here's what 5% looks like. Here's what 10% looks like. And so they all start to compress, which makes sense. But you can see the Kirpich is much lower down at the bottom end of or the shorter end of the flow path. And that's really because of that sheet flow calculation that's in the velocity equations. NRCS lag equation is a very popular equation. I've seen that if they're not using the velocity equations, most of them are using NRCS lag equations. So we looked at it, and it was developed by Marcus in 1961, and it was for areas less than 2,000 acres. It's a little bit bigger basin than what I was looking at, but it still fit the description. Plus it's very popular. It has a CN value in there. There are it's basically an equation that was formed on basin surface data or surface conditions. And so when you plot these out and compare it to the velocity equations, you can see they're very high in time of concentrations. And that's what I see a lot of people that use these in hydrology reports end up some very high time of concentration equations. It almost misses here. This is for 5%. It almost misses all of the velocity equations. It starts about halfway down on the velocity equations. But Federal Highway Administration, this is HEC 19, developed this adjustment factor M, and they applied it because they felt that they decided that farmland, they're not always working with farmland, which is where NRCS was working with, or what Marcus developed his time of concentration equation on was agricultural type land. And so they added some impervious factor, which is this M value, and they added a main channel or man-made channel factor to this. And so if you take these factors, I already had a relationship for CN values for impervious factor. I know what that is with the table that I just created. The main channel, it's a little bit of a speculation, but the fact is above a CN of 80 or better, or 85 especially, there's going to be a lot of man-made channels in that type of development or in that type of surface condition because there's a lot of impervious surface. So if you take those factors and you add that to the lag equation, the lag equation then now falls in place with the velocity equations. This is what it looks like at 2%. And of course, there's a systematic crossing of the velocity equations. Here's 5%. And of course, here's 10%. Another equation I'll took a look at was FAA equation. And this equation is sometimes used, or it's quite often used in urban conditions. But it was an equation based based on surface data or surface condition. There was no channelization consideration in this equation, but it was done on airports, and it was developed by the Army Corps for FAA. And I really like this equation because if you see when we plot it out compared to the velocity equations, it has almost identical shape, the curve, as you will, to the velocity equations, but there's no channelization factor. And if anybody, I've done a lot of research looking at this equation. If anybody has a channelization factor for this equation, I'd certainly be interested in talking to you because it almost fits these velocity equations. I've found that without that 1.8 factor in there, it drops down real close to these velocity equations. In fact, Texas had a modified FAA time of concentration equation. I think they use 0.7 something as a factor rather than the 1.8, and it almost puts these a lot closer to being in line. But I wanted to just show this as a comparison because this is what happens when you don't have channelization in your time of concentration calculations. So looking at this small watershed runoff response, the time of concentration comparison graphs between the velocity equation and channelized empirical equations convey a systematic intersect for each related surface coefficient. Empirical equations provide a lower time of concentration in short flow, and the empirical time of calculations provide a higher time of concentration on your longer basin flow paths. Runoff time is on small basins exhibits a transformation from surface attribute to flow dominant, surface attribute flow dominance to a channel attribute flow dominance. So I just referred to this as timing outside the channel and timing inside the channel. And you can see that in that pattern just by the way they cross. So we're going to look at another, so what can we do to create something that's a little more predictable for time of concentration? So what I did was cut off the areas that were in question. You can see here that I cut off the velocity equations where the lag and the Kirpich equations dominated. And the lag is in green and the Kirpich is in blue, and they almost intersect the velocity equations almost at the same place throughout that pattern there. This is for a 2% slope. This is for a 10% slope. So it's very consistent where they cut those velocity equations off at. So if you take that, I came up with this equation that fits those types of curves or those types of equations. And this one's set up for impervious surface. And it's basically just has the length of flow path in it, percent impervious surface, and the slope in there. And here's what it looks like plotted out for a 2%. So now you have all four equations. I call this the uniform time of concentration equation, but this is for a 2% slope. So the red lines are kind of mimicking the pattern we're seeing where between the velocity equations and the empirical equations. Here's 5% slope. It even looks a little better for 5% slope. Here's one for 10% slope, so it still fits. And you can see this is basically the same equation, but now I'm using the CN value. And I found this one to be even more accurate and more precise as far as matching those curves. But anyway, all we have is a CN average in here and percent slopes and of course the flow length. And I remember this is a CN average. So what, in some cases, some of your soils may not be an average. Well, they're not going to be an average. Most soils, you can see the red line, the CN average fits very closely to the B-type soils here. So if you've got other soils on here and you want to adjust for those types of soils, then you would use this particular equation to adjust. And of course here, depending on what soil type you have, you would plug in the values into your X and your either a 0, 1, or 2, and then you would convert everything over to a CN average at that point. This is the one for C value, and you can see it's the same format, same type of equation. Again, the C value is not as well defined, and so I had a little bit more difficulty trying to come up with a pattern. So what I did was I took, beside the earlier chart you saw from Pennsylvania State, I grabbed another one from Iowa, and you can see now that they've got flow depth 5, 10, or 100-year storm event. They got the same categories that CN value has. And so there's a lot of these charts across the country, but everybody's just slightly different. So here's one for, this one's for Colorado. And again, it's slightly different. It's a little bit slightly different, but it's got a 2, 5, and 10-year storm events. So to me, the C value is a little more complex. It's got flow depth in it. It's got, you know, it's got your percent imperviouses in it. And so there's a much more wider range for the C value. Rosmiller came up with an equation using how to actually calculate a C value based on a CN value. And so there's that complex complication. And there's also, I've seen just simple definitions of the C coefficient where it says C coefficient is nothing but runoff over the rainfall event or the rainfall depth. And that's how they calculate the C value. So there's no, I haven't found a real standard for that C value yet. But anyway, so now I compared it. I used actually 10-year storm events for those areas and plugged that into the equation and see how it looked, see how it compared. So this one's for Pennsylvania and at a 5% slope. So this is taking into consideration more flow depth because I'm using not just my typical 3-inch flow depth. I'm going up to whatever that area is. I think Pennsylvania was like 4.5 inches for a 10-year storm. So I use a 10-year storm here just to compare it. This one's for Iowa at 5%, and it does fairly well with that equation. And this one's for Colorado, and it does a pretty good job too at 5%. And I didn't show the 2 and 10%, but it shifts with those same type with the slopes and matches up pretty good with the other equations. Of course, we've got the soil types related now to the C equation. So you can adjust the C value based on your soils, but the adjustment's much smaller here. You probably don't need to make an adjustment unless you're going to be less than 0.5. You can see they kind of converge as you get above 0.5 on the soil type. And again, if you're a B-type soil, which there's a lot of places that's all they are is B soils, C average works very well. I wouldn't do any adjustments for it. In fact, it lines up almost right over top of it. This is the equation you would use to adjust the C values. All right, so this is my add-on here. So what is the relationship with Archimedes and the watershed surface runoff? Well, for years, we've known that there is a relationship, and we've seen time area diagrams, and there's almost in these time area diagrams, there's almost a standard ratio. You can see here on this graph that it almost follows a ratio, but the problem is it depends on the physical system itself. So each drainage basin is going to be a little bit different. So each drainage basin would have its own little ratio. But once you know it for a particular drainage basin, you can almost say there's a linear relationship there, a ratio there. The other thing that has been known for a while is watershed time to equilibrium, the TC, where the entire watershed contributes to the runoff. This is where pretty much where it starts to get into the channels at that point. And you compare that to the time of concentration. So if you did the ratio of time of equilibrium or time of concentration, it is very, very small compared to 1. It's a lot less than 1. Then it's probably a surface dominated flow. If the time of equilibrium is a little bit closer to 1, then it's more of a channel dominated flow. And we just showed that. So what would Archimedes do to exploit these basic information that he had, the truths there of what we call hydrology? First of all, he would circumscribe the upper and lower boundaries, which I showed you in that one graph. He would circumscribe that and say, well, we know time of concentration has to fit somewhere within these two boundaries. And that's where, that's the same thing he did pretty much with pi, put the circle between two sets of polygons. And the other thing is now he's going to establish a relationship, and this is a relationship that's been established by Marcus, who did the one time of concentration between the length of flow path and area. And this is in the engineering handbook, the NRCS engineering handbook. And then the last thing he would probably look at is knowing the fact that the time of equilibrium over the time of concentration ratio um, changes from a dominant surface condition to a dominant channel condition time. Uh, he would establish that those confluence that you see between time equations with the dominant flow types would show up where the intersection occurred, and we showed that in several of those graphs between per pitch velocity and lag and velocity. And not that he inspired me to do this, but I'm just saying that was kind of a comparison, a quick comparison of probably a guy that well known in history for his mathematical skills, and I always admired him for what his thinking. He was the master of um, inductive and deductive logic. There's no question about it. Any questions we have here? I'm certainly open to questions. This is pretty much it. I do have a paper on this if you're interested in the paper. And I haven't explored all the equations out there, but if I live long enough, maybe I'll explore a few more equations.
Yeah, this is a really, really interesting presentation. Thank you, Kaji. This I like it very much. I have a couple of questions, but before I ask you the question, I open a floor to ask the questions from the students and some other participants. So the guys, do you have any other questions? Any questions to the Ken? You can type the questions, or you can just unmute your microphone and start directly asking.
Yeah, I can't see the typing. Should I pull down my screen here?
I think there is a chat box at the end, at the bottom, so you can.
All I see is my screen.
So if you do not have any question, I mean, it is really, really interesting. By the way, a couple of question. So you eventually came up with a unified equation, right, Ken?
That's the name I gave it. I mean, the idea was I was looking at 3 or 4 equations there that seemed to exhibit similar characteristics. I mean,
Exactly.
we've got probably hundreds of these time of concentration equations, as you well know.
Right. So if eventually it looks like all these equations are predicting somewhere, in the close value. So you came up with a kind of universal equations, like just fitting with the based on the equation, based on the mixing of the, all these equation, right? UTC, you mentioned.
Yes, I tried to, because what I was able to show is
Yeah.
all these equations may be telling us the same thing.
Right.
And everybody, I mean, they're named after each developer of this equation. And what I've seen is that those equations work well for the watershed that they were developed on. And so they're not very portable. You can't take them
Yeah.
to other watersheds and say that it's going to work well on that watershed. Only portable equations are the velocity equations, and the velocity equations are very portable, but they're very difficult to apply because nobody knows their length of their channel, the size of their channel. I've yet to find anybody who can define sheet flow, going out in the field and say, well, this is where sheet flow starts and this is where sheet flow ends. So it's a very difficult application, but it's very portable equation.
So you what you did is, I mean, let me try to refresh myself just for my understanding. What you try to bring it is you have a carb number for the different land use, and also you have a different Manning's roughness given for the same type of land use, right? So you try to bring all these a variation of carb number, Manning's roughness into the single platform and try to analyze, right? For example, the original NRCS equation does not use any Cobb number and just rely on the Manning's roughness to estimate the time of concentration, right?
Right. I mean, we know there is a relationship
Yeah.
in these surface uh, curve numbers, in these C values. We know there is a relationship just because
Right,
they're
right.
tied to percent imperviouses. We know they do exist. And so I
Right.
just showed that. I made a comparison.
So when you, I mean, what you did, like, let's say, the time inertial equations just to rely in the seed flow, shallow flow, and the channel flow, and they just adds up. And in their equation, it's just like a slope and roughness, right? Manning's roughness.
Right.
So you estimated time of concentration from that equations. And in the meantime, you try to relate with the similar type of the land use having certain curve number, right?
Right.
And then come up with a chart and the plot. So the users can essentially, if they know the curve number from your chart, if they know the curve number but they don't know the Manning's roughness, they can use that chart based on their curve number information to get the time of concentration, right?
They do, and the reason being is because I've tied everything back to an impervious surface.
Right. So can you explain a little bit, how it will be beneficial? One quick benefit that I see from here, from this discussion, is that from your research is that, having there are a lot of equations, and the users are really getting confused which to use, which not to use. Now you're showing that essentially these all equations are same. I mean, there is not much difference. So either you can use this universal equation just to get avoid and confusion, or you can if you have a curve number information but you don't know what exactly Manning's roughness is this, then you can transfer that curve number to come up with the time of concentration. So basically this is one quick benefit, but besides that, can you justify the goal of doing this research?
Well, I mean, to me, one of the benefits of making this comparison between those coefficients, those different coefficients out there, is the fact that people use these are coefficients that are used quite frequently in hydrology, in the hydrology software, in the hydrology itself. And most time of concentration equations don't actually compare it to the same coefficient that's used in the hydrology software. And what I've seen in a lot of the hydrology reports is people don't have that relationship. They don't relate the time of concentration coefficient to the coefficient they're using in their hydrology, and therefore they're not comparing an apple to an apple.
Right.
So in these equations, I'm using pretty much the same equations like the SCS method uses the CN value. There's a rational equation that uses a C value. These are common coefficients that everybody understands in hydrology, but I can tell you that most people don't understand how to use time of concentration equations because some of the developers of these time of concentration equations, like the Kopech equation, it has its own value, it has its own K value, and it doesn't relate to a C value or a CN value. And this now I've got a relationship there, and so now you can actually use that equation depending on what you're using within your hydrology. And so there's always a disconnect. People aren't using the same coefficients between hydrology and time of concentration. And hopefully this kind of eliminates that problem in interpretation.
Before I ask you another question, I mean, there is a one concern, one question from one of my student, Prabhakar. He's asking, like, can I get the link of paper related to these slides? I'm very much interested to know about this equation. I think we can share these slides to be sure, and and also the paper. Yes, I mean, you submitted, you gave us one paper, right? We
Sure. Yes, sir, I did.
So basically I can share with him, right?
Yeah, no problem. Heather, I think I sent that to you, and Heather, I don't, anybody who's interested in this,
Yeah.
anybody who has some additional information to elaborate on this, what I've done, I'm more than interested. My email's down there at the bottom. My phone number's down there. Call me or email me with anything that you want to question or add or change.
So the answer is yes, Prabhakar. I'm going to send you paper as well as his PowerPoint presentations. So you'll be getting that. Um, I, we have time, right? I mean, I have a couple of questions. Actually, so you mentioned like a different return periods. In its one point, you just explained, you just mentioned that 10-year return period. Did you analyze everything for 10-year, or you analyze for 5 year also?
Well, in the velocity equations, it's got the P2 in your sheet flow.
Oh yeah, this is 2-year return period. Yeah.
And so that's based on depth. So that is going to be dependent upon the area that your P2 is, your 2-year depth. And so I used a 3-inch depth there. Now the questions come up with other engineers in the past. Well, what about depth? And so my equations don't really take into consider depth, but I can show you some graphs where the confluent changes, and I've found that if I increase by a half an inch of depth in my velocity equations, it changes the time by like 1% for every half inch I add. For every half inch I reduce, it changes by 2% the time of concentration. So it's very small change, but the depth. I've talked to other professors, and they're saying, well, maybe we need to take consideration depth, and depth is a consideration when it comes to calculating time and calculations. But I used 3 inches, and so the only reason I used the 10 inches because that's the maximum. Usually you're doing your designs around that 10-year storm.
Okay.
And that's the maximum the C value or the rational method pretty much analyzed or was developed around. Anything above that, that's why they have the factors for a 25-year storm is 1.1 and then 1.2 for 50. Yeah. And so those parts, I think, is just an extrapolation of what they were actually studied out in the field.
And also, you mentioned somewhere you reduced your length of seed flow and overland flow by 10% for each impervious change or something like that. So is there any rational, or are you?
Other than that equation that Dr. McCurran developed, I think it was what 15 something there, where you have length divided by, where is that? I based it on that. I based it on his principle. His equation works well, like I said, for pervious areas, but when you get in impervious areas, it kind of blows up on you, that equation.
So basically, you took that paper to come up with that conclusion to.
Right. I took the basic philosophy that he says we need to reduce.
Did he specifically say 10%?
No, he did not. So I am making the assumption that there it is. L equals 100 times the square root of S divided by N. So that's what he's saying the length should be. But what if you use this or try this equation, then what happens is on the very impervious surfaces, this L blows up to like 1,000 or 2,000 feet. And so it wasn't really practical.
We can assume that your assumption was more or less correct because, when you plot the graph, all these equations are fitting together. They are overlying with each other. So that means your assumption is not bad. Anyway, if your assumption was too far, then they probably.
Yeah, and all of them say it should be less than 100 feet for sheet flow because it messes up your calculations if it's more than 100 feet. And I find that to be true. So that's why I took the 100 feet and started from there, because when you when you calculate out the impervious, when you get down to the very pervious surfaces and use his equation down there, then that 10% reduction almost fits. It comes in line with the impervious surface at that point, because you end up with 30 feet and 20 feet down at the lower end.
This was much interesting to me because at some point to my students who are doing a senior design project in our in undergrad classes also, I used to ask them to use a different time of concentration and then come up with and show me and compare and see me, because there are so many equations and we would like to see where the real values and which equation actually represents the actual scenario. So that's the reason that I wanted to ask them to use the different equation, and it was always it relies on the user's decision eventually. I mean, we have to make our own decision, and based on the data available and based on the the equations developed earlier. So one more questions to you.
But I can tell you the velocity equations here are, NRCS equations. The part that's in debate is the sheet flow. This is, if there's anything that describes where a tail wags the dog, sheet flow wags the time of concentration here. You can make time of concentration say anything based on the sheet flow. It dominates it until you get into larger watersheds. Then it becomes such a small factor that it doesn't matter anymore.
By
But
the way, one quick question again. Can you, based on your experience, do you have any experience that how much time of concentration estimation will differ? You know, if you assume slightly more seed flow length or slightly less, because it says that 100 feet seed flow literally should be less than 100 feet, right? So
that's
anything
what
above then
makes
is it's a shallow concentrated. But in the reality,
I'm
I don't
basing
know.
on
So
their
it may not
research.
be always 100 feet. So we assume this is 100 feet, and rest of the, let's say, out of the 600 feet, rest 500 feet is shallow concentrated flow. So how is it going to make a difference in our actual computation?
All right, so there is not much difference between shallow flow and channel flow. I
Right.
can show you calculations, and it doesn't make much difference in time for shallow flow and actual channel flow. What
No,
makes
I'm
the
talking
difference is that
shallow and sheet.
sheet flow is what makes all the difference in the world on small drainage basins. So that's why they came up with this 100 feet limitation.
Mhm.
And so they're saying even on pervious surfaces and depending on the slope, you need to really reduce the sheet flow even more. In actuality, sheet flow is hard to determine. It's going to be only an inch. It can't be more than an inch deep. And so when does that happen, or when does that occur out in the field? Nobody really knows.
Right. Um, let me have one question more. I think. Do you have any question, guys? Here is Niraj is also here. A couple of students are here. Do you have any other question? Otherwise, I might ask him because I would like to take this opportunity to
I
interact.
think, sorry, Dr. Sharma, like I joined very late and I was in the office meeting. So, I think you can go ahead and I'll try to, find some questions later.
That's fine. Thank you. Um, Ken, again, you just demonstrated in various slides that you took some data from the Colorado. Sometimes you took the data from the Iowa, just for the roughness, or maybe from the for the sorry,
For the C
yeah, C
values
values,
seem to
runoff
be
coefficient.
right. The C coefficients. The C coefficients seem to be area particular.
Okay. So when you relate that C value with the imperviousness, percentage impervious, so did you just follow certain given by the Iowa, Colorado, or some other location, or did you speak globally?
I use Pennsylvania's because it was sort of in the middle.
Okay.
It, Colorado's a kind of a arid type um, type of environment, so they don't get a lot of rain out there. So their C values seem to be different.
Hmm.
Iowa was a little bit higher. They seem to get a little bit more rain, I guess, because they're near the Mississippi or whatever. But they seem to get a little bit more rain. So I just took something kind of in the middle when I used that for my comparisons. I was using the Pennsylvania C values.
So my another interesting point is concern typically for you is can we just do some kind of experimental data collection or some kind of actual uh, data and then try to see whether we can really replace all those equations with your universal time of concentration equation or not?
I think
That
I think there. I don't have access to some of the studies that were done in developing some equations.
right.
There's a couple professors down at Auburn that have studied some basins and compared
Dr.
the
Jing
different
Fang, you're talking about?
pardon.
Dr. Jing Fang in Auburn University?
He's one, and then there's Cleveland. I think is another one that I'm
Oh,
not
okay.
sure where he's at. But they did a. I researched a study that they did, and they took several equations and tried to compare them.
Right.
But what I don't know is I don't know that they were comparing. They were just taking the raw equations. They didn't take in when they did NRCS. They didn't take in the IF factor, the channel factors and the impervious surface factors. I don't think they did that to their equations.
Mhm.
So I'm not sure that they did their research compared it apples to apples, is what I'm saying. But if I had their data, the information, basically just their runoff information, because that's all they did was take the actual watershed runoff information and then calculate it, then compared that actual runoff to their time of concentration equations. And so if I had that data, I could actually just make that comparison to my equations too, and see how those equations held up. And that's basically what they were doing. I think they took about 10 time of concentration equations and compared, and some of them, and they showed how far off they were. But it was a pretty big watershed basin they did it on. It wasn't a small watershed basin.
By the way,
A lot of research on a small one.
are you thinking to use some other time of concentration equation? There are so much in a textbook. Sometimes it's so overwhelming. The number of equations are so much. And they are developed in a different location, different area, different constraint, and different.
A lot of them I see have their own, like it have their own little their own coefficient. Like a lot of them have an n value, but it's not Manning's n value. They says it's a different n value. And so they all create their little coefficient based on their watershed that they did their study on. And that's the problem I find with a lot of time of concentration equations.
So that's why you just focused on those four, right? You do not have any plan to extend.
I didn't want to try to have to go convert somebody else's n values over to Manning's n values, and plus I didn't have all that information available to me. But those four equations, in my experience, those are at least two of them are the primary equations that are used in almost all hydrology, especially velocity equations. Everybody uses that. They don't know how to apply it, but everybody uses velocity equations.
Yeah. Anyway, I mean, this is a very interesting presentation to me. I believe many of the students who are other people who joined in this meeting enjoyed it. And I'm so grateful for you to have you here. Student,
I'm thankful for the invitation, and the questions and any comments don't have to stop today. They can certainly, like I said.
Yeah, I'm interested to continue some interactions and discussion in future also. By the way, Hithar, did you receive any questions in the Facebook Live or something?
No, I don't have any questions from Facebook right now.
Okay. I mean, I know there are few participants here because, they are probably busy and this is the summertime doing internship and the job. So, but anyway, I believe they will enjoy your presentations. They get some insight from the materials that you are presenting here.
Yeah,
So
if you look at it, this is
continue
just a
interaction
start.
with you.
This is definitely some information to start a lot bigger debate and a lot bigger
Absolutely.
discussion on the subject.
I'm more interested to explore a little bit more because, in the past also, I was looking for those time of concentration equations from the textbook. And in a textbook, there were even more than 10, 12, 15, whatever. And I was trying to, at some point, I was thinking, to try to evaluate all this time of concentration one by one, in our region, and see which equation is going to do better. So basically, I was thinking in your line. So I'm interested to continue some interaction with you for the possible extension of this kind of research in future.
I would be interested too, and if somebody wants to expand a paper on the subject, I would certainly be willing to help them on that subject. So I can tell you when I took hydrology back at YSU, the professor I had at that point says, here's the equation you need to use for time of concentration. Just plug the values in and that's it. And that's what I did. And that's what I did for the first 20 years of my life. So I didn't understand it until after I started looking at hydro reports after a while and says, gee, you really, there are more to these time of concentration than just pulling them out of a textbook.
Right, Ken, we can have this kind of discussion. We can continue to have such discussion in future also. Heather, do you need to officially conclude our program now?
Sure, I just want to thank everybody for coming, and our next Alumni Lecture Series program will be on June 25th at noon. Carla Matusi from the Office of Career and Academic Advising will discuss personality branding on LinkedIn.
So
So thank you, everybody, for joining us. Thank you so much, Ken and Dr. Sharma. It was very informative.
Thank you.
Hi, before closing the conversation, can I
Right.
maybe ask one quick question? This is Niraj.
Absolutely.
Can we can we have the copy of this presentation so that, because I missed the presentation and I could go over with the presentation later and ask any questions if I may have.
Yes, the answer is yes, because we already have a discussion. I have a, Ken has kindly gave us a paper and as well as his presentation. So I'm going to forward you these things. So you'll have
Thank
it. Okay. Thank you. Do you have any more questions? I think he doesn't. So, all right, Ken. All right, Hitler. Thank you so much for organizing this event.
Thank you for the invitation.
Yeah, I'll continue to have interaction with you in the future. So